Let's look a little more at the hardware we use and some of the protocols that make them function. In our network, we have different kinds of networking equipment that has a specific role, which it does and does well, but it only does that one thing. On layer 1 of the OSI model, we have repeaters. I mentioned them before, and even though they're not commonly used, there are still some of them out there. Basically, it receives a signal, it amplifies the signal, and then sends it out again. This is used on long stretches where we have copper to extend how far we can transport the data. We also talked briefly about hubs. We used to use them for our networks some years ago, but they have mostly been phased out now. They are really just repeaters with more than 2 ports. All traffic is sent out all ports. We have no confidentiality, we have no integrity, and it's half duplex and in no way secure. And everything is on the same collision domain. The next step was then we moved on to bridges. Early on we still used the hubs, but to ensure our collision domains didn't get too big, we would then put a bridge in between the collision domains. We could have a hub with 20 users, then a bridge, then another hub with 20 users, then a bridge, and so on. The collision domains were manageable, and what the bridge did was, it separated the 2 traffics, left side, right side. If you look at the image over here on the right, all the workstations on the left would get all the traffic from the other workstations, same thing on the right. And unless they specified traffic to a device on the other side, traffic would never make it over there. Which I guess was a slight step forward, but still very unsecure. Switches then are just bridges with more than 2 ports. Every single port on a switch is its own collision domain, which then fixes the biggest problem with CSMA, which were the collisions. Since every single port is a collision domain, there are no collisions. And a standard switch can range anywhere from 4 ports to over 500. Some switches can technically be layer 3 switches, which mean they can route IP addresses, but assume most of the switches uses the MAC addresses of the clients to direct their traffic. On the switch, we need to be sure we have good security. If a port is not in use, we should shut it down. We should ensure that all the ports are in the appropriate VLANs they need to be in. That means if we have accounting and we have HR, we make a VLAN, a virtual LAN, one for accounting, one for HR. Even if they're plugged into the ports next to each other on the switch, they will never know each other are there, because logically they're separated. Shutting the ports down is also one of the things we can do to stop employees from plugging in rogue access points. If all the ports were connected to the patch panels we have next to the workstations and no security was in place, they could easily plug in the rogue access point or even just another switch. So if the port's not in use, shut it down. We can also use the MAC-STICKY command. That allows us, instead of hard-coding the MAC addresses to each port, which would take a tremendous amount of work, we can, for instance, put in the command MAC-STICKY2. That means the first 2 MAC addresses seen on that port will be added to the configuration for the port, and anything else with any other MAC address plugged into the port will not work. We normally use MAC-STICKY2 or 3 because in most cases we have a voice over IP phone and a workstation at least. That is obviously more secure because only those 2 devices are allowed, but still remember, MAC addresses are easy to spoof. We also need to clear the sticky MAC addresses to replace a phone or a computer. And when we're configuring the MAC-STICKY, we can also choose what happens if the number of MAC addresses is exceeded. It can either give us a warning, or it can just shut the port down. We then need to clear the conflict, re-enable MAC-STICKY, and figure out what happened. And then finally, on our trunk ports are the ports we have between switches, we need to enable VLAN pruning. Remember the VLANs were the logically segmented LANs we had, where we split accounting out from HR. And when we do the pruning, we only send traffic for the VLANs that a certain switch needs. So if we have HR in 2 buildings, then the HR VLAN should be transported between the 2 switches in the buildings. But if payroll is only on one of the buildings, that data should never be transported to the switch that doesn't have anyone from payroll on it. So we will prune that VLAN out. A VLAN is a broadcast domain that's partitioned and isolated to layer 2. On the graph over here on the right, you can see we have 4 different VLANs. We have VLAN 23, that's for our voice over IP phones, and we want to separate that out from our computers. That really is the easiest way to ensure that we have good quality of service on our VoIP phones. They get the priority on the traffic, and we have nice clean phone conversations. Then we have accounting. They're on VLAN 1, but the accounting VLAN is only located on switch 1. That VLAN needs to be pruned for traffic for switch 2. Same with the HR VLAN. VLAN 2 doesn't need to travel to switch 2. VLAN 3, on the other hand, both switches have users in VLAN 3. That needs to be on the trunk port. To make VLAN function, we use VLAN tagging. Every network packet is tagged with the VLAN it belongs to. This way we don't need to have a switch for HR, one for accounting, one for payroll. We can use the same switch for all of them, and we just logically segment each VLAN, which makes it for us much easier. It is more secure, we have much easier traffic management, and it's much cheaper. On many switches, they have dedicated ports with higher speeds to connect to other switches. If a normal switch port is a 1 gig port, dedicated ports between the switches can be 10 or 40 gigs, which makes sense. This way the trunk port doesn't become the bottleneck where we have a traffic congestion. But if our switch doesn't, you can just use one of the regular ports. Whereas the ports for the workstations or the phones we would configure as an access port, we would just configure the switch-to-switch ports as trunk ports. And then for each of the access ports, that port would have assigned the appropriate VLANs that it should be in. If we look at the top left computer, the one that has a VoIP phone, that port should be assigned to VLAN 1 and 23, whereas the one at the top right should only be assigned to VLAN 1. And where the switches have a lot of ports, because they are the devices all our end devices connect to, routers have very few, and they should. They have an entirely different job. They would normally be in our data centers in our organizations, or in some cases at the demarc from the ISP. For your home, they're often combined in one box, where the router, a switch, and a wireless access point are all combined into one box. And since routers are layer 3 devices, they forward all traffic based on source and destination IPs and ports. Router is what we use to connect our LAN to the WAN. And in almost all cases, with a few exceptions, the inside IPs on the router are private addresses, the outside IP or IPs has to be public addresses. Every router keeps a routing table, which basically tells it traffic going to this destination should be sent this way. And there's multiple ways that a router can get updates to its routing table. We can configure a static route. A static route is a pre-configured route, something we code into the router. If you're going to this subnet, send traffic to this destination. That's the best path. Whereas with a default route, we can tell a router, send all non-local traffic to ISP. That way anything that needs to go to a public IP is just forwarded to ISP, and they can make their decisions on how the traffic should be routed. A dynamic route is a route that your router has learned from another router using a routing protocol. That could be OSPF, EIGRP, BGP, or ISIS. And all of those protocols uses metrics to determine the best route to the destination. Some of them uses just the shortest path, regardless of the bandwidth. If they see one path that has 6 routers in it and the other has 7, it'll send all the traffic out the 6 router path. But some of the more intelligent ones uses a lot more different metrics, which can include the hop count. It will also look at the bandwidth, the response time, and many other factors. I have talked briefly about how routers have 2 operation planes, a control plane and a forwarding plane. One where we make all the decisions and where we send the data. On the control plane, this is where we keep the routing table, where we choose the route to send the data out and which interface to send it out. This is the part where we have the static route, or the dynamic routes it's learned through its routing protocol. And in the control plane, the static and the dynamic routes are stored in the routing information base. It then strips the non-essential directives from the RIB to build a forwarding information base, which is what the forwarding plane uses to send traffic. In the forwarding plane, the router, forwards the data between our incoming and outgoing interface connections. And it does that by using the network type of a package header. And just like FTP, the control plane is the brains, it figures out where to send it, and the forwarding plane sends the data.